All right, so welcome everyone. Today we have Łukasz Dudziak, which is research engineer at research engineer. Yeah, or scientist.
Not a big difference anyway.
Okay, at the Samsung AI Center in Cambridge. So, and yeah, today he's gonna speak about the challenges of federated and zero-cost NAS. So, where he was one of the co-authors of the one of the first zero-cost proxy NAS papers. So, yeah, without further ado, the floor is all yours.
Thank you, Arber. Thank you for inviting and for the introduction. So, as mentioned, this talk is going to be basically split into two parts, which are mostly unrelated. So don't be surprised if there's kind of like a jump from one topic to another. The first one is going to be about cross-device federated NAS, and I will basically explain in more details what it means and what's the setting and everything. And the second one is actually about the operation scoring in supernet-based NAS when we use zero-cost proxies, but also study some other ways to score operations in this setting. And basically, we will share some insights that we got from our study. So the first part, so this is work which I did in collaboration with Stefanos and Javier from our center. So just to mention the credit where it's due. And yeah, so let's start with a bit of background. Well, neural architecture search, so NAS, I hope most people here should be familiar, but just to align everyone and to be on the same page. So in this particular case, we would be considering a NAS where we have the data set, training hyperparameters, and target hardware given a priori. So these are fixed. We don't really mess with these things. And the only thing that we are supposed to do is we are supposed to find the most efficient architecture from a given search space. So this is basically the most typical NAS setting. So I hope this should be fairly clear. Yes, and more importantly, federated learning. So I'm kind of guessing that maybe not everyone here is familiar. So let me introduce the concept and some main ideas here. So standard training, I think most people should be familiar. So we have a server, we have a neural network, some data set, our hardware like a GPU, we do forward pass, we do backward pass, and use some optimizer like SGD to update parameters. So this is all easy. So what's the main difference with federated learning really is that we still have our server with our nice GPU, but we don't have data. Instead, data is being spread across multiple clients that will participate in the trading. However, ground rule number one is that the data cannot leave each of the clients. This is due to the privacy concerns, GDPR, and so on. So we would like to train on this data, but the data cannot leave the device. However, what we can do is we can communicate the model. And that's basically what we're going to do. So the server, which keeps a global version of the model, basically starts by sending the current version to each of the clients. After that, each client performs local training on their own data. So this is basically repeating the two steps that were already present in the centralized training a couple of times. At the end of the local training, each client will have its own version of the model, and they will communicate it back to the server, where the server will basically try to aggregate them, these individual updates coming from each client back to kind of update the global version that it has. And this process repeats, right? So each cycle like that is called a global round in federated learning. And basically it's like a nested loops, right? So we have one loop that goes over global rounds, and within each global round, we have another loop that goes over data of each individual client. So this is one thing to keep in mind. And there are also two important properties of federated learning. So basically, our clients in general may not have uniform hardware. So this is referred to as system heterogeneity, and it's one of the main problems that we will be dealing with. So it's kind of important to keep it in mind. So like basically in this example, you can see that one of the clients might have some powerful hardware like a laptop, another might be a smartphone, and maybe we even have someone with a calculator doing computations for us. So basically the range can be quite diverse. Second of all, data that each client has might be quite different. So in this particular example, the distribution is actually quite nice. So we can say it's IID distribution. So because each client has kind of equal coverage of the classes. So, each one has a cat, a dog, and a plane. And then like face masks are, for example, present in each of the clients. But in general, that's again, not necessarily the case. We can have some extreme cases of non-IIDness in the data distribution, where, for example, only one client has certain features, like, for example, if just one client had face masks, or even maybe there is a class that only exists on one of the clients. So the higher the non-IIDness, the more challenging our federated learning problem will become. So that's one thing to keep in mind. So I hope that's clear. So following a little bit on that, we can in general distinguish between two main settings in federated learning. One is called cross-silo and the other is cross-device. So cross-silo, a good way of thinking about cross-silo is like if we had, let's say, hospitals that want to collectively train a model. So we have just a small number of clients, but these clients are, like kind of institutions. They have powerful hardware. They actually collaborate on training a model, etc. But they just cannot share data because, it's patients' data, so privacy and so on. On the other hand, cross-device FL is when you actually want to train your model on like a lot of different like mobile devices, for example. So we have hundreds, maybe even thousands of clients. These clients, we don't have such control over them. So we have much more failures. We don't really know if there are any other processes running. Hardware diversity is much higher. We also cannot ask a particular client to train for us. So we just assume that there are some clients available, but we don't really know what these clients are. So in general, cross-device is much more challenging, but it also gives us the opportunity to kind of experience more diverse data. And as you can guess from the title of my talk, our focus will be on the cross-device FL and how to enable NAS in this challenging setting. Okay, so I think that's all when it comes to the preliminaries about FL. So just for the sake of completeness, okay, so why we would like to do NAS in a federated way? Basically, the main reason would be data. So if you have data, then yeah, sure, you can do NAS centralized, right? But what if you don't? Well, then federated learning gives you a great opportunity to actually consider this previously unavailable data in a privacy preserving manner. So that's good. Additional benefit might be that it actually pushes computations to clients, right? So you don't really need to do the legwork on the server. So if you don't have thousands of GPUs, then maybe now you can do NAS. Although this is a bit tricky, right? Because, okay, well, you are not paying the electricity cost, but your clients will be paying this cost. So, you need to be careful about that. Also, in terms of wall clock time, it's probably going to be slower. So if you really care about keep getting results fast, then probably it's not the best option. But yeah, there is also this aspect of pushing computations to the clients. And what are the main challenges? Number one, and this is, I would say, the main one actually, is varying client participation. And I will talk a little bit more about that in next slides. There is also the problem of keeping communication cost manageable. So if you remember, like the server sends model to clients, clients do local training, and then they set back updates. So this sending actually, if you do the math, it might turn out to be quite substantial. So we don't want this to blow up, basically. So this is another thing to keep in mind. Finally, which is kind of a typical problem in NAS, faithful model evaluation might be a problem because of some things that are more specific to FL setting. And yeah, I will also mention that at the end. So varying client participation, the main problem, in my opinion. What is it about? So imagine we have two models, like the ones at the bottom here. So architecture 1, which is kind of complex, nice, and big, and architecture 2, which is very simple and small. And we want to train them given these three clients that we already saw in previous slides, right? So it might be the case that architecture 1, because it's big and complex, might actually be too difficult in terms of computational power to train on some of the clients. So it will effectively have limited exposure to training data because of that. And this might affect, to some degree, its generalization, what we think is its generalization capability, right? So because we train on limited training set, then we just don't generalize so well as we could have. On the other hand, a simple architecture might very well be able to train on all the clients and have better coverage of training data. And because of that, it might appear to be better. Well, it's kind of a philosophical question. Like, should we consider a model better or not in this case, right? It does have the advantage of being able to run on more devices. So perhaps there is a reason to consider it better. But if we're interested in just really trying to understand and score different architectures through their ability to generalize, that's probably not perfect. We wouldn't like to be affected by this fact that some big models might just not have enough exposure to training data, and we might consider them bad because of that. So this is a simple example, but just to give you a more real life data that kind of justify this reasoning, we actually run experiments. So in this case, what we did is we took like 160 models from a search space, which was some MobileNet-like search space, not exactly important right now. And we trained them on, this is all federated learning. So the black crosses are these 160 models when they are trained on all the clients, assuming all clients can train all the models. So we can see kind of the usual trend, which means that models that have higher flops, so are more complicated, they kind of tend to increase in accuracy. However, what we then did is we enabled this kind of tier awareness. So in this particular experiments, we divided our set of models into 4 tiers. You can see them on the plots, based on how many flops a forward pass takes. And then we said that each tier has 25% of clients that kind of belong to this tier. So basically 25% of the clients can run tier 4 or less complex models. Another 25% of all the clients can run models in tier 3 or below, and so on. So to put it in a different way, tier 1 models had access to all the data. Tier 2 models had access to 75%, then 50%, and then 25% of the data. And you can see that kind of as conjectured in the previous slide, as we have more models, larger models, as they have less data that they can train on, the performance actually drops quite significantly. So yes, we asked ourselves, like, okay, what can we do about it, right? So our main hypothesis is that, well, we can use weight sharing. And perhaps if we have word sharing, then this can enable transferring knowledge from low-end clients into larger models. So even though the low-end clients cannot train large models, they can train kind of parts of it. And because we do weight sharing, then this will magically transfer and help boost performance of large models. So in our design, because we still want to keep things kind of lightweight and everything, we decided to go with this single path one-shot. So I hope you are all familiar with it. So it's a supernet-based search method that basically in each forward pass selects a random path. But we made sure that basically clients select paths that are within their computational capabilities. So that's why we call it budgeted. So it's a lightweight method. It allows us to basically train different models and have weight sharing with as little overhead as possible. We also claim that now, okay, so this is fine. So we can have weight sharing because of that. But now different layers are kind of stochastically exposed to training data. So it might be a case that maybe an operation will never be updated by a client. And another operation will be heavily updated. So we also have to take this into account when doing this aggregation. So when the server receives multiple updates from different clients, just keep in mind that now different parts of a model experience different number of data. So yes. Yes. So this is related to challenge 1. Now, if you remember, we have 2 more challenges, which is keeping communication cost manageable. So towards this one, we actually, I think, did the simplest thing that we could. So basically, just don't send the entire supernet, just select a subset and send it. The tricky thing here to remember is that we need to select a subset in such a way that clients can still find models that are within their computational capabilities. But that wasn't a big issue in our case, so I'm not going to talk about it much. Finally, faithful model evaluation. We actually didn't address it directly. I will mention a little bit because we checked how faithful our evaluation is, and I can already tell you that it's actually not very faithful. So rank correlation is low and everything. But we see that it's not a big issue in our case, although it probably leaves some room for improvement. So that's why I'm mentioning it here. Okay. So to be a bit more specific, these are kind of formal equations that we use to define things. So let me quickly go through them. So selecting a random subnet. This is basically, so for each layer L, we have this OL, which is the set of candidate operators. And we just basically want to have a random subset of it, such that the communication cost over all layers and all selected operations to communicate within all layers is below. So communication cost is basically number of parameters. I hope that's quite clear. Single path one shot. Okay, so path through a supernet is basically an operation selected from each of the communicated sets of operations, such that the training budget is below the threshold. So in our case, we used just flops, but it could probably be generalized to other metrics. We just kept it simple because it's not the focus of the paper, really. And then the normalization, you probably don't remember because it was fast, but on the previous slides when I was talking about the FL, like preliminaries of FL, we had this normalization. Basically, the main difference is that now everything is done with respect to individual operations rather than full models. Yes. So yeah, a bit of details. So random subset selection, we did it just by going one by one and removing operations randomly until we are below the budget. With the only tricky bit is that we kind of protect the operations that contribute the least So it's kind of like we always have like identity, for example, right? We don't want to remove identity because we rely on having identities in our super networks to kind of be able to not increase the cost of doing a forward pass, for example. So here, actually, this was a bit tricky. So actually realizing this condition of having a path below a threshold is not very efficient. So I mean, naive way is basically sample a path, check if it's below the threshold. If it's not, resample. But then the problem here is that if your threshold is very small and probability of finding a path below this threshold is very small, then this can actually become quite a burden. We did some experiments, and in some extreme cases, it was even more than 1 second to sample just one path. So because this is going to affect mostly clients that are low end, so the ones that have the lowest threshold, we kind of thought, okay, well, maybe we can actually do better. And so we approximated, it's not exactly the same in the mathematical sense, but it's an approximation where we basically greedily select operations one by one according to a random permutations of layers. And it worked sufficiently well, and it has this nice property that it has constant runtime, regardless of your training budget. So basically, as long as there exists an a configuration or a path that is below your threshold, then you will be able to find it in a constant number of steps. Yeah, and finally, like I said, this is just doing things per operation. But importantly, a thing to note is that now clients have to communicate back to the server how many training examples were being used to update each operation. So before that, we didn't have that. We were just communicating weights. Now we communicate weights and also information of like how often this operation was selected during this path sampling or not. This is just to have more informed aggregation. Okay, so this is a visual summary of our system. So we have this supernet, which is on the server. We send to different client subsets. So these dashed things are the ones that the operations that were not selected for communication in this particular round to a particular client. Then clients select random paths for each batch, send back updates. So like I said, we have this kind of histogram saying, this operation was selected that many times. Some operations were not selected at all because, for example, they were not part of the communicated subspace. And we use this information to update the supernet. And this is really the main heart of our system, which is stage 1, supernet training. We just, for the sake of completeness, we then do the search. So we actually start validating different paths in a kind of, so in our experimental setting, we decided to have one model per tier, but it could be changed quite easily. We kind of don't have much contributions in this part, so it's kind of like we don't care. But kind of importantly, after we identify different models, we also fine-tune them. And this fine-tuning is kind of important to get very good performance. And importantly, it's not training from scratch. So we don't reinitialize models because we hypothesize that this supernet training and weight sharing actually helps with this client participation gap that I mentioned earlier. Okay, I hope that's clear. So let's look at some of the results. So first, this weight sharing hypothesis. So basically, you can see these are some example results. We will see more detailed ones later, but you can see that we have basically architectures that even beat training which doesn't consider clients' eligibility. So this tier unaware setting, especially in highly non-IID cases. So this is really good. We really like these results. And we kind of follow up with more detailed evaluation. So for different experimental settings, we have basically what this is. So we run our search, we found some architectures, and then we test their performance when we initialize them with weights from the supernet, and what if we reinitialize randomly. So in most of the cases, actually, supernet initialization is much better. There are only 2 cases in this whole big table where it wasn't the case, and it's always in tier 1. And just to recap, tier 1 random initialization has access to all the data. So it's kind of like you don't really have this problem for this particular models. However, for example, especially when non-IIDness is very high, so these 2 cases are the primary examples here. Even for tier 1 models, we see substantial gains from weight sharing, which was actually a bit surprising. I can talk a bit later, like what's the intuition behind this, but this is a very strong result, so it's probably worth highlighting. And like we kind of conjectured, tier 4 models, regardless of IID or non-IID distributed data, they always benefit from weight sharing, right? Because these are the ones that when you train them kind of naively, they have the most limited training set. So we kind of see improvements across all cases. Okay, so that's great. Now let's kind of go to comparison with other methods. So we have 2 FL methods, FL-NAS methods. One is fedNAS, one is Spider. They were both designed in cross-silo setting in mind. So basically we compare by either bringing these methods into our cross device or taking our method and running it in cross-silo. So for Spider, there's no code, so we couldn't adapt their method, but we did adapt fedNAS. And so fedNAS uses darts like supernet, right? So it's much more memory hungry. So in one case, when we have like slightly non-IID data, it was a bit better, but with higher memory peak. When we adjusted batch size, it actually dropped below our performance. And then again, like we really have strong results with highly non-IID data, right? So fedNAS in this setting drops significantly, whereas our drop is kind of moderate with just 5 percentage points. At the same time, running our system in cross-silo, it's okay, although it doesn't beat Spider, for example. I'm not very concerned about it because we kind of designed everything with cross-device in mind. So so it's just kind of, you can't have everything. I would say that's the conclusion here. But it's still competitive. It's not broken, like for example, fedNAS with highly non-IID data. So, okay, so comparison with heterogeneous FL. So basically methods that also try to do the same. So train big models that might not be supported on all devices by shrinking them or distilling or doing other things. Well, good summary is that we are better. There is a lot of results here, but we were able to beat pretty much everyone here. However, cost. I guess everyone who did a little bit of NAS knows that the cost is what you pay basically for these good results. So actually, so here cost is not that high, although the main difference is in the number of local epochs that we do in supernet training. And this is related to the fact that we have SPOS. So basically, we need to have sufficiently many forward passes done on each client because each forward pass is a different architecture. If we just, for example, run for one epoch like many FL methods do, then we will just explore like 10 paths on each client, and it just doesn't work so well. So even though, for example, communication cost is not that high because the number of rounds and the fact that we send subspaces of a supernet actually this all makes it manageable. But the computations that each client has to do is actually higher. So this is something that I will admit straight on. Okay. Although, for example, peak memory usage is reasonable still. And compared to FedNAS, which is a NAS method, again, we are not more expensive. It's just that if you compare our NAS to other things like pruning, then yes, then we are more expensive in terms of computations per client. Okay, so that's it. Final remarks. So I mentioned this operation aggregation. So this is this, instead of naively averaging weights, do this averaging per operation and consider how often this was selected. So this leads to improvement of like between 1 and 2 percentage points. So kind of okay. Search space subsampling. So sending half of the supernet turned out to be kind of a sweet spot. And a nice property is that we had both faster convergence, better results, and lower communication cost by doing that. So it's kind of like win-win-win, which is not very typical. Like I mentioned, in the stage 2, so after supernet training, when we start validating models from a supernet, we actually tested it, and the validation accuracy of these models compared to their accuracy after fine-tuning is weakly correlated, so up to 0.3 Kendall tau. So basically not correlated. However, this is enough to avoid selecting bad models. So it's like, okay, we cannot find the most accurate one, but we at least don't pick things that are broken. And this is basically where we're still able to get good results. I mean, I can show you plots maybe later if you're very interested, but that's basically what we observed. However, yeah, that's definitely room for improvement here. If we could find these architectures in a kind of smarter way, but without blowing up the cost, then we could get even higher results. Finally, we assume that we do have validation data available on the server. But in general, that might not be the case, in which case we would need to resolve to basically doing evaluation of models also in a federated manner, which means every time we want to test a model, we need to send it to some clients. And basically, one client is not enough to test it because it just has a subset of data. So this increases communication cost quite drastically. For details, I would invite you to take a look at the paper because it's hard to summarize it. But it's possible to be done. It's nothing that would prevent us from doing NAS in this way. So, okay, that's all for part 1. Some references.
Yeah, so have some questions in between, like.
I mean, we can have questions now if you want, or later, up to you.
Yeah, I guess now if somebody has any question before Łukasz goes to the next part of his talk, yeah.
Yeah, maybe one quick question. Have you considered taking any additional information you have of your devices into account for your architecture selection? Like, I don't know, what is some meta information that describes the devices you have, so that you can measure the correlation between them?
So a short answer would be that we didn't really consider a lot of information. The only information that we assume we have is basically how capable a client is. And that's to ensure that we send a subnet to a client that kind of makes sense, right? So for example, that contains networks that this client can actually execute. In general, because in cross-device setting, you don't have control over what clients you have. That's the assumption. I'm not exactly sure how much you can do. You should probably ask this question to my colleagues who are more familiar with FL literature. Yeah, but like I said, the short answer is that we didn't do too much.
Okay, thanks.
Yeah, I have a follow-up of that are related to that question. So in stage 3 in your algorithm, so actually, so what you, maybe if I understood correctly, you up during search, you update the submodels in your devices, and then you send back an aggregated, I don't know, weights or something like your supernet in the server, right? The server weight.
So stage 1 is supernet training. When we do this, basically I talked primarily about stage 1.
Yeah.
Yes. Then stage 2 is, I mean, it's basically done on a server. So we test different paths, but we test them kind of as they are. So we basically extract a path from a supernet and test it, right, on validation set. No fine tuning, no adaptation, nothing. So what we have, that's what we test. And then we take the most promising ones and we further train them, but in isolation. So this is standard FL training, but we still respect clients' capabilities. So for example, a model from tier 4, after it's extracted from a supernet, it's only going to be fine-tuned on 25% of the data in most cases, because it belongs to the highest tier. So we assume only quarter of clients can train them. So that corresponds to a quarter of training data. Okay, so that's the information you have from the clients that you use, like the models you need to fine tune. Stage 3. Yeah. Okay. Thanks. Another question?
Just one question from me. Hi. Do you think it would make sense to use zero-cost proxies in stage 1 to select the subsets that you think would be the most promising to send out to the clients? That's an interesting question. We didn't think much about zero-cost proxies, but we were considering in general that like how to send a subset of a supernet in a kind of biased way. So basically, for example, send a subset that was the most trained one so far and things like that. But a short answer again is that we haven't done much about that. So I suspect that there should be some scope for further research or improvements by considering better sampling. Here we really used simplest approaches and they turned out to work quite well and were enough to kind of validate our hypothesis. So we are happy with that. Okay. Thank you.
Okay, then continue with the second part of the talk.
Yeah, okay, second part. It should be shorter. So this is perturbation-based NAS. I think this is much more familiar to everyone here, hopefully, because there were already presentations about zero-cost proxies, and I know TNAS also was presented. And then, yeah, so this is along the same line. And again, collaboration with some of my colleagues from Samsung, but also beyond. Okay, so very quick recap. Again, standard NAS, we have data set, some constraints, metrics, set of architectures, and well, after we train them, we have some scores. We want to get the best one. The problem, the most typical one, as usual, the cost of training is high. So instead of training, what we do is we want to have a different way of scoring through the zero-cost proxies. So we have SNP, GRASP, SynFlow, but also NASFOT, TNAS, ZenScore. These days, actually quite a lot. I think with each year, more and more proxies are being proposed. So yes, problem, or well, maybe a thought here. So these proxies are fine, and we know a lot about them. But what we kind of tried to address when we started working on this is that they only give you an indication of like how good a single model would be. And we can use it to guide evolution or some reinforcement learning methods and so on. But if your search space is really, really big, then this becomes a limitation for you, right? So it's kind of, in plain words, you could say that it's not that simple to find a network that would maximize your zero-cost proxies if your search space is very big, which is kind of ironic, but that's kind of what we saw. So what we thought is, okay, well, so can we combine supernet NAS with zero-cost proxies? Because we know that supernet NAS is kind of like trying to encapsulate architectures in one entity. So maybe we can score a lot of architectures kind of collectively, right? So this is more or less the idea behind one-shot NAS, but brought into the world of zero-cost proxies. So, I mean, these days we know that it's obviously possible. We have TNAS, for example, that does pretty much exactly that, and maybe some other papers that I'm not aware. But I will present basically our take on this problem. So what you formally want to do is, from a given supernet, we want to derive a final model in a sequence of steps, where in each step we select an edge. So here we kind of follow the formalism where edges are operations. So on each edge, we want to select just one operation from the candidates in each step. So in a number of steps that's equal to the number of edges, we should have a final network. So the question becomes basically how to find this sequence of what operation to select on what edge, such that the final network is as good as possible. And the problem in the world of zero-cost proxies is that we know that zero-cost proxies work well when you have the final network and want to score the final network. But how do you score these intermediate steps and the quality of intermediate steps in such a way that the final output is as good as possible? So for extra context, we basically consider two basic operations that you can do on your supernet. One is discretization that I kind of already mentioned. So basically select just one operation on an edge. And a complementary operation is perturbation, where we remove an operation from an edge that hasn't been discretized yet. Okay, so now the first thing that we do is we basically thought, okay, well, let's score and try to evaluate different ways of scoring operations. So basically, the line of thinking here is that, you know, like in standard zero-cost proxies works, we often use correlations, and you know, higher correlation means better proxy. But here it's kind of like, okay, so we cannot just correlate things because like it's even hard to answer what to correlate in some sense. So we try to answer basically this question exactly. So what to correlate to, right? And for this purpose, we define this Oracle scoring function that basically says that given a supernet in whatever state and an edge, we want to take, so this operation is supposed to be the operation that's being selected on an edge, right? So we want to select an operation on this edge such that performance of the network, the performance of the best network that would be possible to obtain if this operation was assigned to this edge is maximized. So it's like kind of look ahead, right? So, okay, so if I choose this operation, what's the best possible network that I can obtain? Obviously, this is something that we cannot in practice use. That's why it's kind of magic Oracle function. But this is exactly the thing that we would like to kind of mimic, right? We would like to have a scoring function that produces the same results as this magic Oracle. Also, for the sake of completeness, we define a similar function that talks about expected performance of network after an operation is selected rather than max operation, just because we thought maybe it would give us some extra insights. So these are the two kind of ground truth metrics that we use to analyze things. After that, we basically took some scoring methods from the literature. So we have all the darts, pretty well known. So this is just take operation that has the highest alpha. We have discretization accuracy. So basically, okay, well, just select this operation and train a network, but train the super network, not any of the final networks, right? And then basically, if super network is better, then this operation is better. And also perturbation accuracy. So this is kind of complementary to the discretization accuracy, but we don't do any fine tuning after an operation is removed here actually. So the idea is that if you remove an operation and your accuracy drops a lot, this is the most important operation and you should select this one. Yes, and well, sorry. And since we are also interested in zero-cost proxies, we also have analogical functions where we either discretize or perturb a super network, but we are interested in the resulting zero-cost score of this super network after we modify it. So how did it work out? So like I said, we correlate mostly to best accuracy or average accuracy, but best accuracy is really what we care about. And we have a couple of interesting findings here. So the figure on the left shows a correlation in when we try to discretize the first edge, and then figure on the right is kind of like doing this, what happens when you do it edge by edge, so in the further iterations. But I will mostly talk about the first iteration because I think the differences are the most clear in this case. So first of all, discretization accuracy is actually quite bad. And this we kind of explain by just saying that, okay, this is because your super network is over parameterized. So what we did here is we took NAS bench 2 and we say, okay, well, what happens if we select on one of the edges a none, a skip, and a conf 1 by 1? And well, first of all, is if you actually train them until convergence after each operation is being assigned, then you can see that they all achieve very similar results. And that's just because the super network in general is over parameterized. So even if you select none on one of the edges, it's not gonna change much because your super network still is over parameterized. So it doesn't have too few parameters or anything. However, if you select conv, it's actually harder for the network to converge. And that's the main reason why we saw this very weak correlation to what was considered like this oracle scorer, because very often operations that were making a network smaller were preferred, because smaller networks, in this particular case at least, was resulting in faster convergence, not necessarily to worse results, because, like I said, overall, the network is over parameterized. So this is one failure point that we kind of highlight. Second of all, so perturbation based on accuracy actually turned out to be worse than perturbation based on zero-cost proxies, which was a bit surprising. But we took a closer look. Well, okay, so we actually have a hypothesis more than a concrete answer to that. So basically, we can see that, so when we take a very detailed look at the scores produced by DartsPT, we can see that in general, they make sense. So convolution 3x3 is very often selected. And then, second is convolution 1 by 1 most of the time. However, it does have preference, at least again in this experiment, to select skip connection. So we don't have a conclusive answer why this is the case. But if you read DartsPT paper, they actually show that well, I mean, under certain assumptions, etc., because it's a theoretical proof, but they show that the input to a mix-up layer is actually close to the desired output. So like optimal feature maps that are supposed to be produced by this layer. And that they use this to to justify why alphas assigned to skip connections are higher. So what we kind of conjecture here is that because your input is already kind of close to what you want to have as your output, and basically things like convolutions and etc., which are being added to this kind of act as refinement, then removing a skip connection will actually have the most severe effect on your closeness to this optimal feature map. And that's why we hypothesize is AdartsPT actually has this preference for skip connections. Although, to be fair, we haven't proven it, but at least empirically, that's kind of what we see. Okay, so a final observation from this experiment is that actually discretization in the case of NAS photometry is really bad compared to perturbation. And this was a bit surprising. So we tried to understand slightly better what's happening here. So one of the experiments we ran is basically we started, so we constructed a simplified supernet when we had just two operations to choose from, skip connection and convolution. And then we were varying the depth of this network. And this correlation here is basically as the number of layers increases, we can see that discretization quickly degrades. So this is correlation with like the best possible zero-cost proxy, because we didn't have accuracy, but I think that's not very important. Still, this is an interesting phenomena, I would say. Again, we don't have conclusive answer why this is the case. But from the definition of NASWOT, we know that NASWOT is trying to measure diversity in the linear regions for different inputs. So my kind of, again, conjecture would be that basically when your network reaches certain depth, considering that it's randomly initialized, then at some point you will be just kind of, it will saturate, like basically the diversity will start to be random, right? So like after you pass your input through like many enough random layers, then the distribution will slowly, distribution of values in your activations will slowly become random, more and more random. And because of that, in order to maximize diversity, the preference would become to actually just reduce depth of your network. This is what we empirically see. So basically, okay, so correlation degrades. And again, this is because of skip connections. It's always skip connections. On the other hand, perturbation doesn't have the ability to reduce the depth, basically, because if you will always have an operation that's not skip connection that adds to your depth. So it's kind of like you only compare choices that keep the same depth of your network. And that's probably why it works better. Yes, so that's it. Okay, so this is all when it comes to the analysis of existing proxies. So from now on, it's just kind of building on top of that. So we basically saw, okay, well, NASWOT with perturbation seems to work very well. So let's try to design an algorithm which would try to leverage this. And here the idea is really simple. We basically do what I described earlier. So we start with a supernet. we take edge by edge in a random order, and random order is here to maximize entropy and to kind of have enough exploration. But take edges like one by one in a random order, and on each edge, just try to perturb by removing each operation, measure the NASWAT score after perturbation, take the one that reduces in the largest drop in NASWAT. So we consider this to be the most significant operation. And by doing that, we derive one architecture. However, like I said, we want to have exploration. So basically, we repeat this process n times. And because we have random edge order and also random initialization each time, then we will end up with a number of different architectures that at the end, we just score them using normal NASWAT. So you can think about this whole algorithm as a way to just discover models with high NASWAT scores, really, right? We don't really like, so my point here is that the performance of the final performance of each of the networks will actually depend on how good your zero-cost proxy is. We are more interested here in how to discover good architectures, assuming you have a good proxy, rather than to basically increase fidelity of a proxy with respect to accuracy, which is what you would usually do in other works. But because we saw that NASWAT basically works kind of okay, that's why we that's why we thought that it should be enough. Yeah, so 2 stages. One stage, just produce a couple of architectures, and then from this architecture, simply take the one that has the highest zero-cost proxy. So how did it work out? I would say pretty well in general. So on the Dart CNN search space, I'm skipping results on NASBench2 because, yeah, I mean, you can find them in the paper. NASBench2 is an easy benchmark, so yeah, they are good. No surprise here. More interesting ones, I think, are the ones in larger search spaces, right? So Dart's CFAR10, we are kind of on par with Dart's PT on average performance, slightly behind, although this is training based and we are zero cost. So obviously a cost is an important factor here. But in general, we would say that we are a bit behind on average because our variance is higher, right? Because it's zero cost, so it's kind of less stable. The best case scenario actually is higher, but but on the flip side, or that's average is worse. So then a standard thing to do, so try out on ImageNet. Here we do transfer from Cypher, so we don't search directly on ImageNet, although I think we could have, but well, we didn't. And yeah, again, we have pretty good results. We actually have better results than Dart's PT. So even though on CypherTen we were kind of a bit behind, here it turns out to be much better. We are a bit worse than another one-shot method that does like training-based, etc. But again, pretty fast. And yeah, so TNAS, which is the closest method to us, when they do exactly the same as us, so when they transfer from CypherTen, well, they are kind of behind. But when they search on ImageNet, they are, I would say, comparable, really. Although, like I said, we didn't search on ImageNet. I don't know if that would change anything. So finally, we also tested on MobileNet version. Well, it's proxyless search space, basically. Here, a thing to note is that we didn't implement our method as kind of cost aware. So we just searched for the best performing model without any constraints on the number of parameters, which is kind of unfair when you compare to all these baselines because they did constrain flops. But yeah, well, since our method doesn't allow for that, at least in this version, like we didn't have much choice. So I would say, treat these results more as a proof of concept. So, okay, yes, we can find well-performing architectures in a mobile net search space, but don't necessarily compare them to these methods, because it's not directly comparable. They are more for context, right? So, okay, we don't constrain things. So yes, we find more accurate architectures, which is expected. Our cost is lower, which is expected, and that's it. Finally, I think 2 interesting baselines here as well. So like I said, our method is basically effectively searching for a model that would maximize your zero-cost proxy. So we could ask, okay, well, why not use evolution to do that, right? So just run evolutionary algorithm to maximize NAS or something. So this is what we did in this table on the left-hand side. And as you can see, it didn't work so well. So like I said at the very beginning, kind of paradoxically, it's actually quite hard to find these good models in a very large search space. On the other hand, yeah, with this supernet-based scoring, you can get much better results. The table on the right-hand side is similar one, but instead of doing evolution, it's more like this, what was proposed originally. So just take a sample of models and score them and take the best one according to your zero-cost proxy. So we can see that, as we take more models, we get better results, but still they are not as good as what we can get. Yeah, that's it. Sorry for running a little bit out of time. If you have any questions about the second part, then please feel free to ask.